This is going to be my video over projectile motion, the practice problems in the sheet I made. I wrote focus on here because the camera wasn't focusing. Thought maybe, you know what? Alright, I gotta keep my hands in frame or else it all goes wonky. Excuse me. Okay. So if you pull up the Google document, you'll see the first problem is on one-dimensional motion. You jump off a building 150 meters in the air. Assuming gravity is 9.8, how long does it take to hit the ground? What we have here is a one-dimensional motion problem, meaning we can solve it with our four kinematic equations. These equations are V is equal to VO plus AT, delta X is equal to V plus VO over 2 times T, delta X is equal to VO T plus 1 half AT, and V squared is equal to VO squared plus 2A delta X. The information we have so far is you jump off a building 150 meters in the air. This means from top to bottom, delta Y, I'll use Y because it's vertical. Excuse me, it's 150 meters. Gravity, A, is going to be negative 9.8. How long does it take to hit the ground? Time is unknown. That's what we're trying to find. The initial speed is 0 because we're just jumping, so initial speed is 0. And then final speed is also unknown, but that is not something we need to know. We have delta y, a, we need to find t. Which one of these equations can do that? It's kind of just a matching game with one-dimensional motion. This equation needs v, so not that one. This equation needs a v, that equation needs a v. The third kinematic equation, it's going to be the one we use. Because delta x, v naught, and a, we have all of those. So, oops, rest a little too much there. Plug your numbers into that equation. 150 is equal to 0 times time plus 1 half, negative 9.8 times time. We can choose positive 9.8 here because it'll be weird if we don't. Ugh, I never understand. Gravity is sometimes positive, sometimes negative. Use the value that gets you a positive answer for time. That's why I say. So rearranging the equation, 150 times 2 divided by 9.8 is going to equal t squared. T squared. Oh, almost forgot about that. T squared. That could be bad. So take the square root. That'll give you t. Plug that into your handy dandy calculator over here. And you get t is equal to 5.53 seconds. So that's the first answer for one-dimensional motion. You should try to do the second one. Really easy. Just use another one of these kinematic equations, maybe two, and it'll all work out perfectly. Ooh. Right. Next up, we're going to be doing a two-dimensional motion equation. A marble is launched at a 45-degree angle from the horizon at a speed of 12 meters per second. How high is the marble at its maximum height? So, we have our y-axis, our x-axis. It is launched at a 45-degree angle and makes a little quadratic here. 45 degrees at a speed v is equal to 12 meters per second. When we have a two-dimensional motion, what we want to do is we want to break speed down to its y and x components. We do this by using a little bit of trigonometry. At a 45-degree angle with a speed of v, the y component of velocity, is going to be equal to v times sine theta. I mean, calculus, use our little unit circle there. It all works out. Vx is equal to v cosine theta. That I'm triangles, weird stuff. All right. With that, we can find Vx is equal to 12 times cosine of 45. And Vy is equal to 12 times sine of 45. Sine of 45 is equal to cosine of 45 is equal to square root of 2 over 2. So Vx is equal to Vy is equal to 6 times square root of 2. Voila. Now, the question is asking us to find the marble at its maximum height. That's really just a one-dimensional motion problem. We are looking at the marble as it travels up and down. The y-axis is completely irrelevant. The x-axis is completely irrelevant here, as we're only looking at height. So let's use our kinematic equations. We know the component of velocity. We need to know height, or delta y. That is our unknown. We also don't know time. We know initial velocity, though, as 0. I'm sorry, I got that wrong. The initial velocity is their y component. The ending velocity is 0, because they'll have 0 velocity at that height. 0 vertical velocity, that is. These are our kinematics equations. We can look at equation 1. V is equal to V0 plus AT, or 0 is equal to 6 times the square root of 2 plus 9.8 t. Solving this will let us find the equation for time. Plugging these things in to your handy dandy calculator, do a little mix match. We get t is equal to 0.866 seconds. Now, we can change our unknown of t to 0.866 seconds and call it a day. Well, not quite. We need to find the maximum height. Now, with time on our hand, we can use the second kinematic equation. Delta y is equal to v plus v naught over 2 times t. Putting this together, we get 6 times the square root of 2 plus 0 over 2 times 0.866 is equal to delta y. Use your calculator once more. And we get delta y is equal to 3.67 meters. Voila. That was really just a glorified one-dimensional motion problem when you think about it. But thinking is hard, so I don't do it. Our next the next question for two-dimensional motion is without looking, derive the formulas for time, height, and range of a marble launched at theta degrees with a speed of v. This one is a little harder. Basically, it says we're launching a marble, but it could just be any object, at an angle of theta. It wants us to find how long it's going to take for the marble to hit the ground, the maximum height of the marble, and the range. And it wants it all inside a nice, handy formula. We can do this using kinematic equations. If you think about it, we just did the equation to find the height of the maximum height of the projectile motion. That was what we just did. We used the first kinematic equation, V is equal to VO plus AT, and then we plugged in time to the second equation. Let's do that again, but just keep everything inside its variables. We have, 0 for ending motion is equal to Vy plus G of t. Or you could just rearrange this. T is equal to negative Vy over G. We're going to erase that negative sign because time can't be negative, and negative time is no bueno. But that's just the time from here to halfway. So doubling it, so that'll be the time until it hits the ground again. We get T is equal to 2 Vy over G. That is our time for a marble launched at angle theta. Vy, of course, is just equal to V sine of theta. Voila. Next up, we need to find height. Let me erase this and write down what we just found out. t is equal to v sine theta over g. Another way to find time, that I'm just thinking about, which is probably a lot more useful, is just to use the velocity at the beginning, which is vy, and the velocity at the end, which is negative vy, because it's traveling in a different direction. And just plug that into the second kinematic equation. Negative vy is equal to vy plus gt. Might subtract that, negative 2 vy over g is equal to t. Is equal to, let's erase those negative signs, because time can't be negative. 2v sine theta over g. Same thing, same answer, but if you don't want to, if you think it's a little, iffy to go to the halfway point and then double it, you can just do it like that. Anyway, maximum height. This we'll use the second kinematic equation. The maximum height, h right here, at angle theta, will just be half of the time, because at half time you're at the point, using the second kinematic equation. So delta y, change of y, is equal to the velocity, the y velocity at the top is 0, plus the y velocity at the bottom, v sine theta, over 2 times the height, half of the height, because it's at, the halfway part, v sine theta over g. Multiply that stuff together, you get v squared sine squared theta over 2g. That is the equation for maximum height of two-dimensional motion. Let us erase this, plug that equation up here. H is equal to v squared sine squared theta over 2g. Voila. Hope that was the same equation. That was, right? So it was. I'm not being dumb. Next up, we need to find range. Range is going to be a lot easier, actually. Because in the x direction, there's no acceleration. The distance from here to here is just going to be the speed of x times time. That's it. Because, no acceleration, none of that funky stuff. Just traveling in this direction until the marble hits spot. We would do air resistance, that's too, ugh, lame, weird. So speed of x is going to equal to, I'm sorry, speed. Delta x is going to equal to the speed of x, which is v cosine theta, times that equation for time, t. Expanding it out, we can get r, I'll just call delta x r, is equal to v cosine theta times v sine theta times 2, because I'm just putting this over here, over g. See that? Now this is where the sort of fancy part comes in. This is equal to v squared sine theta cosine theta 2 over g. 2 sine theta cosine theta already over here. Using some fancy trigonometry, this is equal to sine of 2 theta. You could prove that, but I'm not going to because it's awful and hard and I hate it. But just kind of trust me. You can put this into this, bringing our equation down to v squared sine 2 theta over g. Easy peasy. It's equal to v squared sine 2 theta over g. That looks kind of like a u. Let me fix that. Voila! Equations for time, height, and range of two-dimensional motion. Really not that hard, but I would definitely recommend going over this on your own paper. See if I did anything wrong, derive it yourself, get a better feel for it. It'll make two-dimensional motion a lot easier. Now on to the harder questions. The first question is, in a firing range, shots are taken at different angles and different directions. The speed of the bullets is u. Find the area in which bullets can spread. Originally, this might make no sense, but you need to think about it in 3 dimensions. Okay, we got our z-axis, our y-axis, and our x-axis. What he's saying is that at a set speed, the speed of u, he is just launching bullets at any type of angle and in any direction. So it's in what direction? It means around the z-axis, and launching them at different angles. Wah 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 wah, all around. This is going to make a circle of possible points it could land at. Any sort of a. Let me try to draw a good diagram here. Around the z-axis, at any angle from the z-axis, you could do it at any angle, up, down, around, whoosh. So really, the circle is going to be based on the maximum range. In order to do that, we need to find the maximum range that a marble can go at, and that'll kind of make the radius for the circle, if that makes sense. The radius is going to be, be maximum distance away from the center. So the maximum radius will be the maximum range that you can get away. And then we can just plug that into our circle equation, which is pi r squared, and find the total, area in which bullets can spread. I hope this is making sense. If it's not, there's always Discord. So, doing on this, we need to find the maximum range. The maximum, not range, excuse me, maximum range. It was range. I'm so dumb. Oh my god. The maximum range of a bullet. If you remember our equation, R is equal to V squared sine 2 theta over G. You'll note that because our speed is set, we have a speed of U. This is a constant. This is a constant. The only thing that can change is theta. So what angle for theta will make sine 2 theta the greatest? If you think about your unit circle here, the greatest value for sine is 1 when you're at a 90-degree angle. So sine of 90 will equal 1. That'll be the largest value of r. That'll be at 45 degrees. So 45 degrees to double it, then you get 90. You get sine of 1. It all works out. So we have our maximum range, which is u squared over g. That is our maximum range, and as such, the maximum radius for the spread of bullets. Let's plug that into our circle equation. Pi radius, which is range, u squared g squared, pi r squared, is equal to pi u to the fourth over g squared, or c. All right, let's go on to our second equation. A projectile is projected at an angle theta from the horizon. The tangent of elevation at the highest point, as seen from the position of projection, is. This guy likes to use a lot of fancy, complex words to make him sound smart. Reminds me of myself. But really, it's super simple. You have your arc, your quadratic of motion, y-axis, x-axis. It's just asking for, at the highest angle, highest point, what is the tangent of elevation from the position of projection? It just means if you have a point at the origin to here, what is this angle? I'll call the angle alpha for now. So we launch it at an angle theta, and we want to find the angle alpha from top to bottom. It's actually asking for the tangent of the angle, and you'll see why soon. Tangent makes it so much easier. The tangent of alpha, that is going to be equal to TOA opposite over adjacent. So we're going to want the opposite over the adjacent. When you think about it, the opposite at the highest point, this is going to be equal to h. This is going to be equal to adjacent 1/2 of r, because h is like at the halfway point, so it'll be half of r. It's a quadratic. So nice. So this will be 1/2 r. So the tangent of alpha is equal to h over 2r. No, 1/2 r, my bad. Or 2h over r. Multiply top and bottom by 2. So that is what we're looking for. Let me just write that again up here so that I have more space to work with. 2h over r. Because we're just dealing with our general variables, we're going to need to use all of those fancy equations we derived last time. If you can remember, height is equal to v sine squared theta, v squared sine squared theta, my bad, over 2g. That's going to be what h is equal to. And r is equal to v squared sine 2 theta over g. Because we want 2h over r, let's just go and say 2 times h, 2v squared sine squared theta over 2g over r, v squared sine squared theta over g. Let's simplify that down. Multiply the top and bottom by g, you get rid of this, you get rid of this. These two things cross out, bam, bam. That leaves you with v squared sine squared theta over v squared sine 2 theta. V squareds obviously cancel out. Sine squared theta over sine 2 theta. Sine 2 theta, if you can recall, is equal to 2 sine theta cosine theta. That's kind of like a cheap cop-out, because like that is a trigonomic identity. Most people don't know. So just kind of keep that in mind when dealing with projectile motion. Sine squared theta, sine 2 theta is equal to 2 sine theta cosine theta. Anyway, knowing that, you can mark out bam, bam. Sine over cosine is tangent. So this is equal to tan theta over 2. So when you put it all together, tan of alpha is equal to tan of theta over 2. Which means when you have a graph, if you take the point at the origin to the highest point, the angle is going to be half of the angle that you launched it at. This, of course, on the sheet, the answer to this is B. So question 3 asks us, let T1 and T2 be the times of flights of a projectile for projections at two complementary angles, for its horizontal ranges are. The product of times of flight, T1, T2, is equal to, in terms of R, any one of these things, A, B, C, D. Two complementary angles, that's going to mean angle of theta, and an angle of 90 minus theta. That's just like the definition of complementary. And it wants us to find the times for each of these, multiply them together. The equation for time, t, is equal to v sine theta over g. That, we'll just call this, in fact, t1, because it's already in terms of sine theta. Bam. T2 is going to be v sine 90 minus theta, because it's a complementary angle, over g. Sine of 90 minus theta, that, if you know your trigonometry, is equal to cosine of theta. It's I know that one's, I find trigonomic identity problems a little cheap because like who knows all of them, but that's probably because this is the second time I'm recording this, because the first time I just got the answer massively wrong. T1 times T2 is equal to V squared sine theta cosine theta over G squared. Now, if you think about it, this looks kind of like another equation. Oh, what am I saying? It wants us to find this in terms of R. R is equal to V squared sine 2 theta over G. Is it G or G squared? It's G. Okay. We can expand this to be 2 sine theta cosine theta. And well, you know, these two things look awfully similar, except it's missing the 2 and it's missing the G. Basically, if we want to put this in terms of R, we need to say R divided by 2 and also divided by G if we just divide 2g over, that's going to be v squared sine theta cosine theta over g squared. This is equal to this, meaning r over 2g is equal to T1 times T2. And that is answer D, bubble D. Excuse me. Okay, so that is all for the multiple choice questions. I know they were a little hard. They're going to be harder than what the AP test has for you. The AP test won't make you rely on all these trigonomic identities, everything. But I hope that they kind of let you get a better feel for projectile motion, better feel for range, height, time. Next time we're going to be doing actual AP questions. They'll be a lot easier, trust me. You're going to feel like a genius when you do those. Thank you for watching. I know this was a long video, but I will see you in the next one. Peace.